Welcome back. Section 3.5 Applications of Determinant. This is a very small section. Chances are you have seen this particular application in your course in differential equations. In case you haven't seen it there, here it is. Okay? It's called the Kramer's rule. Say you are given a system in n equations and in n variables. So you have a square system, linear system equals b1 through bn. Linear system of n equations in n unknowns. Let capital A be the coefficient matrix Aij, so that we may write A bold case x. Bold case x is for a list of all your variables, if you remember, equals bold face B, which is nothing but the output column. If determinant of A is non-zero, the theorem says there is a unique solution given by x1 equals determinant A1 over determinant A, x2 equals determinant A2 over determinant A, xn equals determinant an over determinant A. You know what determinant of A is. A is the coefficient matrix. But what is this an? What is this A2? What is this A1? Each of these AIs is a matrix obtained by replacing the ith column of A by B. What that means is, you see, you have these coefficients. Replace the ith column by the answer, that is AI. So if you replace the first column by B's, that would be A1. If you replace the second column by these B's, you would get A2 and so on. That's what AI means. A1, replace the first column of A by B. A2, replace the second column of A by B, and so on. So here is a proof. If determinant is not zero, by the way, this is the requirement. You want determinant A to be non-zero. Okay? If determinant A is non-zero, then we know that A is non-singular. Okay? That's by the theorems we saw in section 3.2. If determinant is non-zero, then you know that A is non-singular. And we also know x equals A inverse B. All right? X equals A inverse B. So I have written down x, and I have written down A inverse, and I have written down B. If you remember what is A inverse, you find the adjoint of A and divide by determinant of A. That is A inverse. So you see A11, that is cofactor 1, 1. A21, that is cofactor 2, 1. So notice, instead of writing A21 here, you're writing here. Remember the definition of adjoint of matrix A, okay? And then you're dividing by determinant times B. So that is your actual x. Now how do you multiply across? Multiply this way and then to B. Multiply this and then to B. Okay? So xith element is you multiply across with B. So let's go back. Somewhere here is the ith row. AI1, B1. AI2, B2. A1I, B1. A2I, B2. All the way ANI, BN. Every one of them is being divided by determinant. So that is the ith entry of the product. So notice this is n by n. This is n by 1. So the result will be n by 1. That is a column. A matrix times a column will be a column. So ith entry will be, you go across in this direction, multiply this direction. A1i, B1, A2i, B2, all the way ANI, BN. Notice you are dividing by determinant A for each multiple. So xi, that is the ith entry, A1i, B1 over determinant A plus A2i, B2 over determinant A all the way ANI, BN over determinant A. You have a common denominator of determinant A. So A1i, B1 plus A2i, B2 all the way to ANI, BN, that's the numerator. This is your xi. Now let's understand the numerator. So if you remember the theorem, xi should have determinant A in the denominator. We got that. Is the numerator now we want to understand. Suppose AI is the matrix obtained by replacing its ith column by B. Then determinant AI is precisely this. Ith column. So you are using expansion along the ith column, and that's exactly what this is. Okay? We have proved the theorem. So the numerator is determinant of AI. Okay? Here is a bunch of equivalent statements, very important. You saw such in one of your previous sections. If A is non-singular, so this is equivalent. A is non-singular, then AX equals 0 has only the trivial solution, which in turn implies A is row or column equivalent to identity. The linear system AX equals B has a unique solution for every matrix B. Unique. Okay? That's like saying only one solution. A is a product of elementary matrices. Determinant A is non-zero. Very important that you remember this. The following are equivalent. Write these statements down. These are only 6 statements. Every one of them is equivalent to the other. That means you can say A is non-singular. Oh, determinant has to be non-zero. Or oh, A has to be equivalent to IN, row equivalent. Oh, the linear system AX equals B has a unique solution. Or AX equals 0 has only the trivial solution. Or A is a product of elementary matrices. They are all equivalent. Saying one is like saying everything else. So every one of this statement is very important that you understand and remember. Okay. Here is an example to use Kramer's rule to solve. Here is your system. A is the coefficient matrix. B is the output column. First, make sure determinant is non-zero. Kramer's rule applies only when the determinant of A is non-zero. So, we are expanding using row 1. 2, that's 2. The sign for 2, its location is 1, 1, negative 1 to the 1 plus 1. Drop this column, drop this row, whatever is left over, its determinant. That's with 2. I'm expanding along row 1. Next 3. Write down 3. And then keep track of the sign. 3 is row 1, column 2. So negative 1 to the 1 plus 2, row 1, column 2. Drop the column, drop the row, 2, 3, 2, negative 1. That's the leftover matrix. Plus 1. Sign for 1. 1 is row 1, column 3. Drop the column, drop the row, 2, negative 1, 3, negative 2. That's your leftover matrix. Find the determinant in each case. Assuming I have not made any mistakes, please check. My answer is determinant A is 25. Please check. Now, Now we are ready to use Kramer's method because determinant is non-zero. What does Kramer's method say? X1 is, first the denominator is determinant of A and the numerator is determinant of, for X1 replace first column by the B column. First column has been replaced by the, so that's A, that's the B. Negative 4, 1 should sit here. Negative 4, 1. Everything else is the same. Okay, check again. 3, negative 1, negative 2, 1, 2, negative 1. 3, negative 1, negative 2, 1, 2, negative 1. So what changed? The first column became B. For X2, the second column became B, negative 2, 4. Negative 2, 4, 1. For the X3, the third column became B. All right. So A remains the same. You see, A1 replace first column by A. A2 replace second column by A1 replace first column by B. A2 replace second column by B. A3 replace third column by B. All right. Find the determinant of each of these matrices sitting on top. Denominator is determinant A. Okay. Denominator is determinant A. So I hope it was not too much back and forth. I hope you understood. Make sure determinant of A is non-zero. 25 is the determinant of A. Now start successively placing B for the first or the second or the third column. The first or the second or the third column. Find the determinant in each case. I have done this calculation. Please check. By now you should be masters of determinant calculations. Determinant of this is 1. Determinant of this is negative 38. Determinant of this is 46. You have solved for x1, x2, x3. That's all in this section. Try these 5 problems from section 3.5.